Hi, and welcome back. So let's dig right into closures. So let's go ahead and create a standard closure. So here I'll use a string for a local variable x. Then we're going to define an inner function, which is simply going to print x. So x is a non-local variable, which means that inner and x is going to form a closure. And then we're going to return the closure from the function. So now we can call outer and assign the result back to fn, right? So fn is now a closure, and it means that we can look at things like the free variables, right? And as you can see, x is a free variable as expected. It's this x over here. We can also look at the closure, the dunder closure property, and it tells us, again, it's a tuple, right? Just like the free variables is a tuple. This is a tuple. There's only one free variable, so we only have one thing, one object in here. But it's telling us that this label is actually pointing to a cell object, and the cell object points to some string object at this location. Now we can actually look at the memory address of x from within outer and inner. But we've got to be careful with string interning, because we may have two different objects that are not pointing to a cell, and yet they'd both still be pointing to the same string. And that's because of string interning, which happens automatically in Python. And I don't want to use integers either for my variable, because as you know, integers like 1, 2, 3, and so on are also singleton objects, which means that I could have two different variables, two different labels, but they'd both be pointing to the same object. So that wouldn't actually show anything. So I'm going to use something that I know isn't going to get reused, and I'm going to use a list for that. So let's go ahead and recreate our outer function. This time I'm going to make x equal to some list, let's say 1, 2, and 3. And now I'm going to declare inner, right? And if I do this, I just want to show you first 1, 2, and 3. And then what I want to do is I'm going to print the hex value of the ID of x, right? And then here, and actually we could make that also x, that will still be a local variable because we have an assignment. And I want to show you that we'll end up with different IDs. So let's just go ahead and run that. Let's say fn is equal to outer. Okay, so we have that. And now if we call fn, we see that, and I need to return the closure. All right, sorry about that. Okay, so fn gives us this memory address. So that's the memory address of x in outer, which is a local variable to outer. When we call fn, we're going to call inner essentially, and x is going to be a local variable to inner. It's not a free variable because it's a local variable of inner, and so we should get a different memory address, and indeed we do. If I hadn't done that, if I'd said Python, okay, here, and Python here, and did the same thing, you'd see that we actually ended up with the same memory address. And that's because of the string interning that we discussed in an earlier lecture. So I'm going to go back and use a list. Okay. Now here, I am not going to recreate the variable. I'm just going to reference it. So I'm going to say y equals x. Okay. That's just referencing the variable. It's on the right-hand side. So now this is going to be a closure. And I'm going to print the ID of y or x, it doesn't matter which one, over here. Okay, so let's go ahead and run this function again. So we're going to call outer, and so we have now this memory address. This is the memory address of x. So the memory address of essentially this thing over here. But remember that fn is a closure. Okay, so if we look at that, it's telling us that the free variable x is pointing to some cell at some memory address, but the cell itself points to a list object at this memory address over here, which you'll notice is the same as the memory address that we printed from here. So Python does the double hop for us. When we request the memory address of the variable, it knows, yeah, there's a cell in between, but it's going to dereference that and find us the final reference. Okay, in this case, it's this one over here. So now we can call fn, and you can see that fn printed the memory address of y. Again, it did the double hop. Y is technically pointing to the cell, but it returned the end reference. Okay, so this is the last one over here. So as you can see, this X and this X are both pointing to the same object at the end of the day. Once the double hop is done, they're both pointing to the same object, and that's because they're both pointing to the cell, and the cell points to just that single object. And so because of that cell, we're able to have two labels in two different scopes essentially be the same thing, right? They're pointing to the same cell that points to that final list. So now let's write a closure where we can actually modify the free variable. So we're going to start with the same example we did in the lecture. So we'll do an outer. We're going to set a count variable, which is a local variable currently. And now we're going to declare an inner function, and it's going to make count that's in ink a non-local count. What does this mean? This means that this count and this count are the same. In other words, this is a shared scope, right? This is a shared label between two different scopes. So count is going to point to a cell, right? This count is going to point to the same cell, and that cell is at the moment pointing to 0. Here we can then say count plus equals 1. So now we're just adding 1 to count, and we're going to return the new value of count. And of course, we're going to return the increment function, right, from outer. So we're returning the closure. So we can see that things are a closure. Let's go ahead and call outer and assign its result to fn. And we'll see that fn has some free variables and has a free variable count. Yeah, that label count was the free variable. In fact, we can also look at closure on fn, and we get that this free variable is a cell. Basically, it's a pointer to a cell, and the cell points to this integer object. Which integer object is it? Well, it's the one, it's 0, right? That's the one right now. In fact, we can look at hex of ID of 0. Since we know that 0 is a singleton integer, it's a singleton object in Python, we should get the same memory address back. And indeed, we do. All right? Because it's a singleton object. So now, let's go ahead and call the closure. So we're going to call fn, and we see it returns a value of 1. Well, what happened is that count was 0, right? Count was pointing to the cell that was pointing to this object. So when we referenced it here, when we said count equals count plus 1, right? This was the same thing as saying count equals count plus 1, or almost the same thing. Count equals count plus 1. Then it actually referenced count, which is 0, added 1 to it, and then stored it back in count. So now it's 1, and it returned 1. But remember that we can't modify an integer. An integer is an immutable object. So what happened, in fact, is that the cell changed what it was pointing to. So it's no longer pointing to 506 FEC50, which is 0. It's now pointing to an object that contains the value 1, right? And so we can see this if we call closure. Again, on the function, you can see that the memory address has changed. Here it was FEC50, now it's FEC70. And indeed, we can look at the memory address of 1. Since we know again that 1 is also a singleton object, we get the same memory address, FEC70. So this is how you are modifying this non-local variable, this free variable, from inside the closure, right? And because both of these counts point to the cell, once outer has finished running, which means by the time, let's say, I call fn, well, outer is finished running, which means this count over here is gone. It's no longer, its scope is gone. However, the cell it was referencing, this cell, is still being referenced by the count that's inside of ink, right? That's in the closure, I should say, of ink, not inside ink. It's not a local variable. It's in the closure that ink that we have here with ink. That cell is still referenced by that closure, so that cell still exists, and it's still pointing to whatever value it is. Initially, it was pointing to 0, then we changed it, then pointed to 1. If we go to 2, if we call it again, it will point to an object with integer 2, and so on. So we saw how we can change the value of a free variable from inside the closure. But another question might be, well, can we change that from another function that's not the closure itself? Can we do that? And the answer is yes, we can certainly do that using this kind of construction. So let's go ahead and again create an outer function. I always need to have this wrapper function in order to create closures. We'll see a little bit later in this video that you can still have variables or labels that are shared between scopes, but without actually having a closure, right? And that's really just a slight modification of an example that we'll do in this video. But first, let's see how we could do something like this. So let's go ahead and let's do the same thing as before. But now I'm going to create this increment1 function, and it's going to make a non-local count. So now it's saying that this count and this count are the same, right? So now we can say count plus equals 1, return count. And I'm going to do now another function, inc2. And it is also going to say non-local count. So basically it's the same code. I'm just going to copy paste that. Okay. So what's happening here, as we saw in the lecture, this count, and this count are all pointing to the same cell, right? It's the same label, or it's different labels that are just the same variable. So these labels are in different scopes, but they're all pointing to the same thing at the end of the day. So they're pointing to that same cell, and the cell is pointing to currently 0. And what we're going to do here is we're going to return both of the closures, right? These are both closures. We're going to return inc1 and inc2 in a tuple. So now we're going to unpack the tuple that we get back by calling outer, and we're going to assign it to fn1 and fn2. So you'll see that fn1 is a closure, and it has free variables. So let's look at its free vars, and let's do the same thing with fn2. And you'll see that both of those closures have that label count. And in fact, the count labels are both pointing to the same cell. Let's take a look at that. fn2 done the closure. And as you can see, the first one is pointing to this cell, and the second one is pointing to the same cell. And of course, the cell is the same, and it points to this object right now, which is the memory address for 0, because that's what count is currently, has a value of currently. So now if we call fn of 1, or fn1 I should say, then we get 1 back. And if we go ahead and rerun this, you'll see that the cell has stayed the same, yeah, but the value that the cell is pointing to has changed. It's now that C70, it's now that integer 1, right? And of course, since it's the same cell for fn2, it's obviously pointing to the same thing. So this is why when we call fn2, right, we're calling the second closure, it's going to do the same thing. It's going to increment the count by 1 and then return it. Well, it's the same object, right? So what is the current value of count? It's 1. So that's why fn2 now returns 2. So we were able to modify the count that's basically referenced by this closure from a different closure, this one over here. And that's because we created these two closures in the same scope, referencing the same outer variable. So that's why we were able to do that. Now, I want to contrast this with when you create closures in different scopes, right? So here we created two closures within the same scope that reference the same variable, okay? Now, let's go ahead and do something else. So let's define a simple closure. We're going to call this power of n. So n is local to power, right? And then we're going to define an inner function that's also going to take a variable, let's say x, and it's going to return x to the power of n, right? So this is why I called my outer function power. It doesn't really matter. But end of the day, this is a closure. This is n, which is referencing this n over here. So n is pointing to a cell, which is pointing to, right now, no value, right? It doesn't have anything, but it is pointing to a cell. And then we'll return inner, okay? So we can see, we can now call power, and let's call this square, okay? And we'll pass in a value of 2. We're going to be squaring. So power of 2, remember, is going to return a function that will take a single parameter, And when we call that function, it will take that parameter to the power of whatever n is. Well, n we're specifying now is equal to 2. So if we do square closure, I'll skip the free vars. We know what the free var is. It's n. So n is something that's pointing to this memory address, this FEC90. Now, because again 2 is a singleton object, I can actually figure out that 2 is what's stored at that location, right? This is the same memory address, okay? So now we can call the closure. Square is a function, right? If you look at square, it's a function, right? Which is this inner function that was inside of power, but of course it's got a little bit more because it's a closure. So now we can call square of 5, right? And we get 25. Now we can do something else. We can say cube equals power 3, right? So now cube is a different closure. It was created by a separate call to power, which means that the value for n equal to 2 and the value n equal to 3 here have nothing in common. They're not the same n, they're not the same cell. In fact, we can look at it this way, right? And we can see that the cell address that's used in this closure is this cell address over here, which is different than the cell address that square uses, right? And this is pointing to a value of 3. In fact, we can look at the hex of ID of 3, and you'll see that it's this same address here, 506 FECB0. Okay, so now we can call cube on 5, and we get 125. So you can see that these two closures were created from the same outer function call, power, but it created two different scopes, right? The free variable scopes were different. The free variable in this case was pointing to this cell, and in the second case it was pointing to a different cell. And that's because when we called power the first time, right, it created a scope, a local scope for the power function. When we created it the second time, when we called it the second time, it went ahead and created a new scope for that call, right? Every call gets a new scope. So because there was a new scope, the closure was created within a new scope each time as well. So they're different closures, right? They don't have the same scope, they don't share anything. Lastly, let's look at the caveat that I mentioned in the lecture. And this is where you inadvertently create labels that are actually shared between scopes. So in the lecture, I mentioned that you can run the code that I'm going to type either directly in the module or inside a function. If you run it directly in the module, you're not actually going to be creating closures, because you can have shared labels, right? Labels that are shared across scopes without having a closure, right? That can happen in different kinds of circumstances. So let's take a look at doing this, but within a function, so that we can actually use this closure here, because it tells us that there's this indirect reference. So it's easier to see what's going on. So let's create this adder function, and it takes in a parameter n. That's going to be what we add to, but let me define the inner function right away, then you'll see what we're doing here. Return x plus n, okay? And then we're going to return inner. So what does this do? Well, the closure is going to take in a single variable, because it's a function that requires a single variable x, and it's going to add n, the free variable, so whatever n is, right? And it's going to return the sum of the two. So now we could say add underscore 1 equals adder 1. So what does this mean? This means that the function inner is going to have a free parameter n, and n is going to have a value of 1. Then we can call add underscore 2 by making another call to adder, and we can do add 3, making another call to adder, and you could do this, you know, for a few more, but I'm going to stop there. So you'll notice that these are different scopes each time. We're calling the adder function. So 3 different scopes here were created, which means that the closures were created inside different scopes. So the ends, right, in these 3 different closures are not the same ends. They're not the same cell, right? In adder 1, n here and n there share the same cell. In adder 2, n and n share the same cell, but the cell between adder 1 and adder 2 is not the same. Same thing with adder 2 and adder 3, right? So we can define these, And in fact, we can take a look at what those cells are by using the DunderClosure property. And as you can see, we have 3 different cells, right? A98, A68, and B168. Okay? So 3 different cells for these 3 different free variables, which makes sense. We created them in different closures. So we can say add underscore 1 to 10, we get 11, add underscore 2, so add underscore 2 on 10 will return 12, and add 3 on 10 will return 13. So that works as expected. Of course, when we see code like this, or code like this, typing the same thing again and again and again, we don't want to type the same thing. So immediately, as developers, we want to try and reduce this and simplify it, and especially avoid repetitiveness, right? So instead, we might think, well, let's do all this creating, a loop. So let's go ahead and do that. So I'm going to create an empty list that's going to contain my closures in this time, my functions, but they're going to be closures. And then I'm going to do a loop for n equals, in range, this isn't Java, for n in range 1 through 3, right? We want 1, 2, and 3. So we'll go 1 through 4. What do we want to do? Well, we want to append a function that's going to be basically this inner function over here. So what I'm going to do is I'm going to use a lambda. And lambda is going to take a single parameter. So basically, I'm just doing this inner function here, right? So lambda is going to take a single parameter, and it's going to say x plus n. But what n is this? Well, this is the n that is in here, right? It's the same n, but in 2 different scopes. So this is a label that is basically shared between 2 scopes, right? So we are going to be creating that cell. So if we do this, then we've just created now 3 things in here, 3 functions in adders, and I'm not calling them closures. They're lambdas, and they have this n that is bound to the same n that we have in the loop, right? And that n exists, it got created. But what is the scope of n, this n right now? It's the global scope. So this n is basically the global n. Now I can't show you this cell using this DunderClosure because the functions in adders are not closures. Because this n was actually referencing the global n, not a local n. So this is technically not the same thing. So we don't have a closure here. And so this we can take a look. I mean, we can look at the first function in adders, and we don't have anything for closure. It's not a closure. There are no free variables. It's not a closure. But this n and this n, right, and this n over here are still all the same. So if I run this now, then it's not going to work as expected. If I run 0 on 10, what do I expect it to do? I expect it to add 1 to 10 and then therefore return 11. But when I execute that, I get 13. Now I'll explain that in the lecture, why that's happening. But it's not very apparent here what's going on. You have to kind of know this. So instead what I'm going to do is I'm going to wrap this inside a function so that I will be creating closures when I call these lambdas, because then the n is going to be a local variable to the outer function. So now I'll have a closure. So let's go ahead and just do this. So I'm going to take the same code right here, and I'm going to call this def create adders. Okay? And I'm going to just do the same thing, but now I'm going to return adders. Now, what is an adders? Well, we have this function, right, that's defined inside this function, and this n that happens to be the n that is a local variable of create adders, right? N is a local variable of create adders. This is a function nested inside this function with a free variable. That is now a closure. And so I'm going to return a list of closures. So we can do that, and now I can say adders equals create adders. So now go ahead and create the adders. So essentially we've done the same thing, except that instead of adding it directly here by running within the global module itself, I've done it via a function, which means now that my adders list contains these lambdas that are actually closures. So if I say adders 0 closure, you'll see that now we have a closure. And you'll see that the n, right, that's the free variable in the adders, is pointing to this cell over here, B2E8. If I look at adders 1 closure, then the n is also pointing to the same cell, right? As expected. We knew this was going to happen because this is a closure that is being created that references the same n every time. It is no different than what we did over here, right? We had two closures that reference the same count. This is the same thing that's happening over here. We have the same n, right, being referenced every time. So this n and all the n's that we have in the three different closures we create in this loop are all pointing to the same thing, right? So we can look at the third one as well, and as you can see, it again is pointing to the same cell. However, what is the value of n? If I call adders 0 on 10, okay, it's now going to call the first closure. Now at this time, it's going to evaluate the function. So it's going to evaluate what's inside the function, this x plus n. So x it knows, we just gave it 10. But what is n? Well, it has to go look it up. So it says, okay, what is n? So I'm looking at the first closure. So it's going to look at this cell, which is the same as the other ones. And it's going to say, well, what's in there? Well, it's whatever object is at this memory address, which you'll notice, of course, is the same for all three because it's the same cell. What is at that memory address? Well, it's 3. Why? Well, the loop ran, so n was 1. So in the beginning, when we ran this thing, it was pointing to this cell, and the integer object would have been whatever the memory address is for 1. Then the second iteration ran. Now we changed n to 2. What does that mean, we changed n to 2? It means that we changed this reference to be an object that contained 2. The cell stayed the same, but it changed what it was pointing to. Which means that as you change the value of n, all the closures, well, whatever the cell is that they use, that's changing as well, because it's the same cell, right? So that's why when we call now add a 0 to 10, we get 13 and not 11 as we were hoping to do. So that's a bug that you can very easily introduce into your code. Now, one thing I didn't mention in the lecture, and I'll show you here very quickly, is how do you solve that problem? Let's say you do want to do this and you do want it to work properly. Well, again, you have to think about what happens when Python creates a function versus when it evaluates it. So the problem is that, right, when we're creating this function over here, it's not evaluating n. It's just saying, okay, n is going to be this shared thing. I'll look up the value for n when you actually call the lambda. Right now, we're not calling it. We're just defining it, right? So we need to somehow be able to capture the value of n as the function's being created. Because if we wait until the function's evaluated, then it's too late because those n's are bound to each other. And if we change one of them, it will change the other ones as well. So a trick that you can do here is to maybe say y equals n. And instead of adding x plus n, we're going to add x plus y. Now, why does this work? This will work. Why? Well, when we have this, right, we're basically setting a default value for y. If we don't specify the value for y, then Python is going to use the default. When does the default get created? Remember, we discussed that before, right? Because there were some caveats there as well with defaults. Defaults get evaluated at creation time. So when this lambda is created, the default value of n, whatever n is going to be used. So when n is 1, y will have a default value of 1. It will not have a default value pointing to the cell. It will have a default value of 1. In the next iteration, when n equals 2, it will have a default value of 2, not n, 2, right? Because Python does not see this as a free variable. It's not a free variable. So in this case, we're actually not even creating closures. We're just creating functions. Let's take a look. So let's go ahead and let's say adders equals create adders, right? So now we've got our adders. What is contained in our adders? Well, again, we have three functions. They're lambdas, okay? So they look very similar to what we had over here, right? Create adders locals lambda, create adders locals lambda. The only difference is that, first of all, they are not closures. If we do closure, we get nothing back. And if we try and look for the free variables on 0, you'll see that we have no free variables. That's because it's not a closure. There is no free variable in this lambda. So by the way, now you have an example of a lambda not being a closure, right? So lambdas and closures are not the same thing. So we don't have it. Why? Well, because at creation time it evaluated n and put that into y as the default for y. So there's not even a mention of n in the body of the function. There's no free variable. There's no closure. What this means, however, is that by the time we call this function, the default value for y is already set. It's 1, and that's not going to change. So if we send in 10, we indeed get 11 back. Of course, this is a lambda that can take two values. So if we really wanted to, we could say, you know, add as 0, 10, 5, and that's going to return 15, right? Because we've now changed the value of y instead of letting it use its default. But if you don't, it's a default, you don't have to specify it, you get that. And if you get adders 1, 10, you get 12, and so on. So that's how you can fix the problem if you really want to be able to do something like this. Don't use a closure, right? If you use a closure, you're going to have a common n. So if you don't want that, don't use a closure. A common trick is to use a default so that you get the assignment at creation time and not a closure, not a free variable that gets evaluated at runtime, at call time of the closure. All right, so thanks for watching, and I'll see you in the next video.